Welcome to video on PLL, third part. We know that there is a block diagram of a PLL having a phase detector, loop filter, and a voltage control oscillator. In the previous video, we were looking at a typical example where VCO is oscillating at a frequency of 100 kilohertz, and we were varying the input frequency around 100 kilohertz. Let us just have a look at. So this is we are looking at the PLL capture and lock range. This is the input frequency. This is VCO frequency, the condition of PLL. So let us assume that VCO is oscillating at a frequency of 100 kilohertz, which is decided by the resistor and capacitor of the VCO. So assume that input frequency is 60 kilohertz, which is far away from 100 kilohertz. Now the PLL is NCNL. So NC stands for not captured, hence not locked. Since the incoming frequency is too far away from the VCO frequency, it is not captured, hence it is not locked. Assume that now it has increased to 79 kilohertz. Even though 79 kilohertz is bit far away from 100 kilohertz, it is still not locked and it is not captured and locked. It has been increased to 80 kilohertz. It's the same condition. 89 kilohertz, still the same condition. Since it is falling outside the capture range, it is not locked. Now assume that it has made 90 kilohertz. Now 90 kilohertz is sufficiently close enough to 100 kilohertz. Now the PLL has captured that input signal. It has generated an error signal such that the VCO frequency is also changed to 90 kilohertz. Now it is in perfect sync with that input signal. Now we say it is C and L. C stands for captured, hence it is locked. The input frequency is captured by the PLL and the VCO frequency is locked to the PLL, the incoming frequency. Now once it is captured, now we can change the frequency from 90 kilohertz to 100 kilohertz. Now we can see it is still captured and hence it is locked. Make it 110 kilohertz as the input frequency. You can see the VCO frequency also changes to 110. Even though it was designed to oscillate at 100 kilohertz, since it is locked, it can change its frequency up to 110 kilohertz. Now assume that now it has become 111 kilohertz. Now you can see VCO frequency is also 110 kilohertz because now it is tracking, it is tracing the variations of the input signal. Assume that now it has become 120. You can see it is still tracing and it is now locked. Now if it has made 121 kilohertz, now you can see it is going back to its original frequency of 100 kilohertz. Now it is no more locked. So we say the PLL has got unlocked. So it is NC and NL stands for it is not captured, hence it is not locked. Now any frequency beyond 120 kilohertz, you can see the VCO frequency is not equal to the input frequency. We say the PLL is now unlocked. Now make it 130 kilohertz. Now it is still oscillating at 100 kilohertz. Now we can see from 90 kilohertz onwards it has captured and now it is locked. So when the input frequency goes up to 120 kilohertz, it is now in locked condition. Now this is the extreme range of the lock frequency beyond which the VCO frequency cannot track the input variations. Now let us do the reverse way now. Now when I'm just going back here now, let me just reduce from 100 kilohertz, sorry 130 kilohertz. When it is 130, it is again still 100 kilohertz. It is too far away from the VCO frequency. That's why VCO frequency is oscillating at 100 kilohertz. The input is at 130. It is now nowhere locked. Now the input frequency is reduced to 121. The output, the VCO frequency is still at 100 kilohertz. It is nowhere locked. It is not tracing the thing. Now assume that now it has become 120. The VCO frequency is still at 100 kilohertz, meaning that it is not locked here since it is out of the capture range. Make it 111, it is still different. Now make it 110 kilohertz. See the change here. Now when the input frequency has reduced from 130, 121, 120, 111, it was not locked. When it has made 110 kilohertz, now it has captured and locked. Now you can see the VCO frequency is same as the incoming frequency. Now we make it 100 kilohertz. Now this is also 100. Make it 90. This is also 90. Make it 89. This is also 89. make the input frequency 80 kilohertz is also 80. Now you can see from 110 kilohertz to 80 kilohertz, so it is in locked condition because it is captured and locked now. So once it is captured, now it is, you can see it is locked here. So if the frequency, if the incoming frequency is 80 kilohertz, now it is in the synchronized locking condition. If the input frequency goes below that, we are in the it is nowhere, it is out of that lock range. Now this is the extreme end of the lock range. If it is 79 kilohertz, the VCO frequency has become the previous frequency of 100 kilohertz. Now it is totally mismatched. If the input frequency is further reduced, so it will oscillate at its own frequency of 100 kilohertz because it is nowhere tracking the variations. Now, the overall understanding of this says that when you are increasing the frequency at a particular frequency, it gets locked, it is captured. Now it is locked till 120 kilohertz. Beyond that, it is unlocked. In its reverse journey, at 110 kilohertz, it is captured as well as locked, and it is in capture range. Sorry, it will be get locked till 80 kilohertz. Anything less than 80 kilohertz, it is get unlocked. Now we can just view these entire set of values what we have displayed here in a single graph indicating over here. I can just clearly see. Now you can see in this graph. So assume that the input frequency is starting here, so that is 60 kilohertz. So assume that the 60 kilohertz and you are increasing the frequency, it has become 70, 80, and you can see now. So when it becomes 90 kilohertz, so you are increase the frequency from 60, 70, 80, it is still not yet captured, so that's why it is not locked. You can see initially if it has to be get captured, it has to come within this capture range. So assume that now it is 90 kilohertz. If the input frequency goes below 90 kilohertz, now it is in the capture range. So once it is captured, it is get locked. Or when it is 60 kilohertz, 70 kilohertz, 80 kilohertz, it is out of capture range. So once it is out of capture range, it will not be locked. So if it has to initially lock it, it has to come within the capture range and then get locked. Now let me go back to previous table and try to find out. You can see it is 60, 79, 80. This is not locked here. You can see this is not locked. 89 also it is not locked. If the frequency becomes 90 kilohertz, now you can see when it comes close to 90 kilohertz, now it is 60, 70, 80, 85, 89. It's not locked. If it is 90 plus, then it is now captured. Now when it is increasing, fine. As long as it is captured, it is locked now. So now it is 100 kilohertz. Now it is 110, 120, 130. So it is keep on increasing as you can see here. So till the input frequency goes up to 120 kilohertz. You can see now. So assume that this is 120 kilohertz. So this is 100 kilohertz, 105, 110, 115, 120. So if it is beyond 120 kilohertz, this lock range ends. So it is no more locked. See here, when the frequency is increased from 60 kilohertz, this is 60 not captured, that's why not locked. 70 not captured, not locked. 80 not captured, not locked. So anything above 90 it is captured, hence locked. 100 it is in the capture range, locked. So now 105 captured and locked. Now you can see even though you are going beyond this capture range, since it is already locked here, it continues to be locking till 120 kilohertz. As you can see in the previous table, if it is going above 120, that is 121 kilohertz, it will not be, of course, that the lock range ends and it will be get unlocked. Now this is 120. Anything beyond this, the VCO frequency goes back to 100 kilohertz. Input frequency is at 121 kilohertz. 121, 130, 150, anything more than this upper lock frequency, now it will be get locked. Now what we can understand here is that the lower capture frequency for this particular example is 90 kilohertz. So at 90 kilohertz it will get captured. So in the forward journey we get lower capture frequency and upper lock frequency. So this is 90 kilohertz whereas this is 120 kilohertz. Now let us come back from 130 kilohertz. I can see in the previous table we went down from 130 kilohertz, 121, 120, so on so. You can see this is 131, it is 120, if it is 1, you can see even for 111, 100. Okay, let us take it as 111 here. This is 120, 111. On your return journey, even though you are within the lock range, lock upper frequency, since it is not captured, because when you are there at 130 kilohertz, it was not locked. So it will get unlocked. If it has to get locked here, first it has to come within the capture range. So now it is 150, 130, 120, 115, 112. Now this is 110. See here, in the previous case, when it is 110, when the input frequencies keep reducing from 130, 121, you can see VCO frequency is operating at its own frequency. When the input frequency comes close to 110 kilohertz, now it is captured. See here, this is 110. Anything less than 110, now it is captured. Once it is captured, the VCO frequency is locked to the incoming frequency. So VCO frequency also changes to 110. Now you can see after 110, if you reduce the frequency to 105, 102, 100, now it is 95, 90, 90 kilohertz. Now it is still in the lock range. You can see it is 89, 80 also locked. So now till 80 kilohertz it is locked, meaning we are here. So this is 80 kilohertz. So we are going from 150, 130. Now this is 110. So on our reverse journey from a higher frequency, we first capture the signal at 110 kilohertz. It will be get unlocked at, as you can see here, 80 kilohertz. So on this journey, we are getting upper capture frequency and lower lock frequency. On the forward journey, we first got the lower capture frequency which we want to capture, and then upper lock frequency till where it is get locked. Whereas on our reverse journey from a higher frequency, first we need to capture it, and then at what frequency it get unlocked. In this particular example, so we have the lower capture frequency as 90 kilohertz and upper lock frequency as 120 kilohertz. Whereas on the reverse journey, the upper capture frequency is 100. Here it is 120 kilohertz is the upper lock frequency. This is 110 kilohertz. 110 kilohertz is the upper capture frequency. This is the lower lock frequency. Now you can just actually write what are the frequencies. This is 80 kilohertz. This is 90 kilohertz. This is 110 kilohertz. This is 120 kilohertz. You can see now we can actually these are the frequencies for this typical example. You can see first it captures at 90 kilohertz. So this is the prevailing frequency. Once it is captured at 90 kilohertz, it will get locked up to 120 kilohertz. So on its return journey from a higher frequency, it will get captured at 110 kilohertz and it will be get locked till 80 kilohertz. So that's what is clear here. When the frequency is increasing, anything after 90 kilohertz, it is get locked here. So now it is captured locked. It is still 120 kilohertz, that was here. So it is captured at 90, locked till 120. On its return journey, it is get captured at 110. It will go up to 80, meaning it is captured at 110. It is get locked up to 80 kilohertz. Anything less than 80 kilohertz and anything more than 120 kilohertz, so it will not be locked. Meaning, if input signal has to get traced, first it has to come within the capture range. So always capture range is lesser than the hold range. So once it is get captured, if you are going above this, it is locked till this upper frequency. If you are going below this, it is locked till lower frequency. Meaning to say, if you want to lock any input signal, first the input signal has to come within this lock range. Always lock range is lower than the capture range is always lower than the lock range. You can see this is capture. Once it is captured, it can be held up to this range as well as this range. So this is called as hold range around f0. This is the prevailing frequency.